In this theoretical framework, white holes might be contributing to the expansion of the universe in a way that remains undetectable under current observational techniques. This could occur if white holes eject non-quantized space, which inherently lacks informational entropy, making it invisible to detection as it seamlessly integrates into the surrounding spacetime. The process begins when information enters a black hole, where it is stripped down to its lowest entropy state. This purified form of space, devoid of all original information and energy, might then be expelled through a white hole. Because this expelled space is non-quantized, completely free of any information, it expands spacetime without any detectable emissions or disturbances. This expansion is harmonious with existing spacetime because it matches the probabilistic expectations of the space into which it's ejected, effectively rendering the process invisible. From a broader perspective, if such white holes are indeed contributing to the expansion of the universe, their effects are diffused over vast cosmic distances. The fluidity of spacetime accommodates this new space, distributing it evenly, and maintaining the overall uniformity of the universe's expansion as observed. The gravitational forces within bound systems like galaxies and solar systems prevent any localized effects from these processes, shielding such systems from the direct influence of the expanding spacetime. However, should a white hole's ejection of space be massive enough to cause uneven expansion at different points in spacetime, we might only perceive this as an anomaly if there's a corresponding disruption in the cosmic background or in the motion of galaxies that can't be attributed to known forces or dark matter. Furthermore, the continuous addition of space by a white hole suggests that it would repel all matter around it, enhancing its isolation in the cosmos. This unique characteristic might also open theoretical possibilities for propulsion and trans-medium travel, where a craft could leverage the principles of space expansion. If a craft could align itself with the direction of space ejection from a white hole, it might harness this expansion for movement, creating a novel form of travel that operates parallel to the conventional motions observed in spacetime. According to the Genesis framework, white holes serve as theoretical cosmic bodies that eject non-quantized space, a form of space devoid of quantized information or energy. This process is intricately linked to how gravity, viewed not just as a force but as an entropic information processing system, operates across the universe. Gravity processes high-entropy information from quantized space into a low-entropy state, storing this data in the continuum of spacetime. When a black hole processes information, stripping it of all its energy and entropy, it reaches a state of minimal entropy or non-quantized space. This purified space, once processed through the theoretical construct of a white hole, is ejected back into the cosmos. The non-quantized space ejected by white holes expands seamlessly into the existing spacetime due to its non-entropic nature, making it virtually undetectable. Unlike its quantized counterparts, non-quantized space contains no energy or information that can be observed or measured with current technologies. This ejected non-quantized space expands the universe subtly by integrating into the surrounding spacetime without altering the intrinsic properties of nearby objects. It matches the probabilistic configurations expected of neighboring quantized spaces, creating a continuous and indistinguishable extension of spacetime. This unique characteristic of non-quantized space to adapt and mirror the surrounding quantum states instantaneously renders it invisible. Since the expansion occurs uniformly and without introducing new observable energy or matter, it does not disrupt the gravitational dynamics within gravitationally bound systems, such as galaxies or solar systems. The gravitational pull and the orbital paths remain unaffected by the addition of this non-quantized space because it contributes no mass or energy, merely expanding the fabric of spacetime itself. The only context in which the effects of white holes and the consequent spacetime expansion might be observable is on cosmic scales. Here, the cumulative effects over vast distances and times might begin to show disparities in our measurements of the universe's expansion rate or variations in the cosmic microwave background radiation. However, detecting these subtleties would require advancements in our understanding and technology, specifically tailored to identify anomalies in the standard cosmological models. The Genesis framework offers a nuanced view of spacetime dynamics, where white holes contribute to the universe's expansion in a manner fundamentally different from traditional notions of matter and energy interactions. This framework encourages a reevaluation of how we understand gravitational fields and spacetime expansion, suggesting that much of what we perceive on cosmic scales is shaped by processes invisible and undetectable due to their non-quantized nature. The Genesis framework integrates the concepts of quantum mechanics and general relativity with a novel twist on the nature of space-time and gravity, particularly in how it conceptualizes wormholes and quantum foam. In traditional physics, quantum foam is conceptualized as a tumultuous sea at the Planck scale where space-time is constantly fluctuating, and wormholes, tunnels through space-time connecting separate points in space-time, appear and disappear. These phenomena are largely speculative and belong to the realm of quantum gravity, a field that seeks to describe the gravitational force within the context of quantum mechanics. Quantum foam and non-quantized space, while elusive and complex, offer a fascinating glimpse into the potential bridges between quantum mechanics and the theory of relativity, suggesting a more unified view of the universe. The Genesis framework posits that what is traditionally considered as quantum foam could instead be understood as transitions of non-quantized space becoming quantized. Non-quantized space, according to the framework, is a highly entropic form of spacetime where information is minimal and the state of entropy is lowest. When this non-quantized space encounters energy, it transitions into quantized space, potentially forming what could be perceived as the foam of fluctuating spacetime at quantum scales. Regarding wormholes, the Genesis framework suggests a different mechanism of formation and stability. While traditional physics considers the necessity of exotic matter or negative mass to stabilize wormholes, the Genesis framework could imply that wormholes are stabilized through a balance of entropic processes, where gravity, as an entropic force, manages the information across these tunnels in spacetime. This aligns with the ER=sign EPR conjecture, which posits that entangled particles, EPR, are connected by wormholes, ER, suggesting a deep relationship between quantum entanglement and the geometry of spacetime. Further, if tiny wormholes are stable and appear naturally, as suggested in some quantum gravity theories, they could indeed serve as dark matter candidates within the Genesis framework. These wormholes would not only contribute to the universe's gravitational makeup but also its entropic balance by facilitating the movement and storage of information across vast distances. Moreover, the hypothesis that a wormhole could have been inflated to a macroscopic size during cosmic inflation introduces a fascinating scenario under the Genesis framework. Such an event would significantly impact the distribution and flow of entropy throughout the universe, potentially explaining some of the large-scale structure formations observed today. The Genesis framework offers a unique lens through which to view these speculative yet foundational concepts in cosmology and quantum mechanics. By incorporating the principles of entropy and information processing into the dynamics of spacetime, this framework enriches our theoretical models and paves the way for new interpretations of phenomena like quantum foam, wormholes, and dark matter. By exploring these connections, researchers could forge new paths in understanding the fabric of the universe, potentially leading to revolutionary advancements in both theory and applied physics.